So what happens when an object has a velocity that's changing? And that's what we're going to take a look at in this short lecture. I actually put together a slide here that has the position of an object at a lot of different times, and the position's given in centimeters, but then I go ahead and convert that to meters on the axis here and then on the motion diagram. And then time in seconds. And the position and times are such that the object is actually getting faster. It's easy to see over here on the motion diagram. If I plot the position of 0 at time 0, and then at 1 second it's at a position of 5 meters, and then at 2 seconds at a position of 20 meters, and so on and so forth, you see on the motion diagram the object's getting faster because the dots are getting spaced further apart. Now if I plot that data on a position versus time graph, we get this shape in here that looks like a parabola. And I could fit a best curve to this as a parabola and take a look at that. Now, anytime you end up having a curving shape on a position versus time graph, whether it's parabolic looking or whatever, you have an object whose velocity is changing with time, because remember, the slope of this graph tells you what the velocity is. So the slope of a position versus time graph gives you information about velocity. So if this object isn't a line, then the slope of the graph must be changing, so the velocity must be changing. And on the next slide, I went ahead and I plotted the exact same graph. This is the same graph as before, but I made a best fit through it, and I had to use a different program to make the best fit, so it's a kind of a different looking graph, but it's the same numbers and everything. The data points are these little slashes here, and parabola fits rather well to here. So I'd like to explain the concept of instantaneous velocity. And the reason why we need it is because the velocity is changing. Back before, when the object's velocity was constant, the average velocity was also the velocity at any instant. The average velocity from 0 to 10 seconds is also the velocity at every one of the times between 0 and 10 seconds. But here that's not true. At the beginning, the graph is kind of flat, showing that the object has a very small velocity, probably 0 velocity around here. And as you go on, the graph gets steeper. And so the way that we visualize this is by drawing something called a tangent line, something that you've seen in your math class most likely. And that if you can draw a tangent line at different parts of this graph, the slope of a tangent line will tell you the instantaneous velocity. In other words, how fast and what direction the object is moving at the time where you draw the tangent line. And this is kind of a mathy way. If you happen to know some calculus or not, or understand the concept of limits, this is how we write out instantaneous velocity. But this symbolism really means that you're going to be drawing a tangent line. You're doing delta x over delta t, like we did for average velocity, but this statement here means make delta t very, very, very small. So that's what I'm going to try to do. I'm going to pick 3 spots, one at 1 second, one at 3 seconds, and one at 5 seconds. And I'm going to draw a tangent line by making 2 dots on the graph that are really close together. And in doing that, I'm taking this delta t and I'm making it small. So around 1 second, I can do that by drawing a dot here and a dot here. At 3 seconds, I'm going to draw 2 dots on the curve, but really close together. And then at 5 seconds, I'll do that again. And I've pre-drawn lines that connect these dots. If you draw a line through these 2 dots, it would look a lot like this one over here. You'll notice I've already drawn this so it connects through. At 3 seconds, this line approximates very well a line connecting these 2 dots together. And at 1 second, this line approximates very well what the tangent line would look like. Now look at these 3 red lines. They're getting steeper as we go on in time, which is showing that this object is getting faster as we go on in time. So the slopes of these tangent lines will tell us how fast the object's moving and what direction it's moving at the times where we draw them. So at 1 second, if I can take this line, and I'm going to move it over here, and I'm going to attach it to my grid kind of like this so you can see the slope more easily. If you take a look, it looks like that this object, I'll use a different color here. It looks like, according to this line, that we're going up about 0.1 meters when we go over 1 second. So one of these boxes goes from 1.2 to 1.4, so half of this is about 0.1. And then 1 second from 1 to 2 seconds over here. So what we have here is a slope of 0.1 meters over 1 second, or just 0.1 meters per second. That's going to be how fast and what direction, so the velocity of the object at 1 second is 0.1 meters per second. And I could do the same thing for all these other lines here. Let me take this one, I'll put it over here. So at 3 seconds, this was the tangent line that we drew. And if I go back here, it looks like when we go over 1 second this time, that this tangent line goes up quite a bit more. It looks like it's going up, let's see, this is 0.2 and then half of a 1, so that's going to be 0.3 meters. So the instantaneous velocity at 3 seconds looks to be 0.3 meters per second, which again is faster. And then I'll do that also with this last line. Maybe I'll take it over here. Yeah, it doesn't really matter where on the grid. I'm just kind of counting how much it goes up and how much it goes over. So taking a look here, when we go over 1 second, from 5 to 6 seconds here, we're going up this much. So this is 0.2, 0.4, and then another half. So that looks to be about up 0.5 meters over 1 second. So the velocity at 5 seconds, an instantaneous velocity at 5 seconds, looks to be about 0.5 meters per second. So the velocity is indeed increasing as time goes on. It appears to increase somewhat regularly. The intervals between these are the same. From 0.1 to 0.3 is 0.2 meters per second. The interval from 0.3 to 0.5 is 0.2 meters per second. So you might not be surprised when I show you the next graph then. If I take these 3 velocities at these 3 times and I plot them on a velocity versus time graph, something that we've done before, but this time the velocity versus time graph is going to look different because our velocities are changing every second. Take a look at these 3 dots and they form a line showing that the velocity is indeed changing the same amount every second. So we could draw a line through this, which is what I'll show here. So here we've plotted the line now, and you see the line goes through the data really well. And I'd like to take a look at what the slope of this line is telling us. So I'm going to try to find the slope using the way that we've been doing it in labs, where I'll take 2 points, maybe take 1 point here and take 1 point here. They're convenient because they're right on the grid. And I'm going to draw my triangle. And if I find the rise over run, and this should be in meters per second, by the way. If I find the rise over run, the rise is a change in the velocity. So I have a change in velocity from here to here, which is from 0.2 meters per second to 0.4 meters per second. So from 0.4 to 0.2, final minus initial, gives me 0.2 meters per second. And if I do the same thing for the run is going to be a change in time. I have a final time of 4 seconds, an initial time here of 2 seconds. So I end up with a change in time of 2 seconds. So now if I find the slope being rise over run, it's 0.2 meters per second divided by 2 seconds, which ends up being 0.1 meters per second squared. And I'd like to talk about what this number means about the motion of the object from before. And this number, what it's telling us, is a little bit more easily understood if we take this meters per second squared unit and take it apart so it actually looks a little more like this. So the slope is 0.1 meters per second for every 1 second. Okay, that's the same thing as this here. So the way I'd like you to read this is from top to bottom. Generally, reading fractions top to bottom is a good idea. That the top of this fraction is a change in velocity. So this fraction means the object will change its velocity 0.1 meters per second for every, which is what the slash line or per means, for every 1 second of time change. So that's how we're going to understand this quantity, 0.1 meters per second squared. We don't think of it as 0.1 meters for every square second. We think of it as 0.1 meters per second, one whole unit, for every 1 second. And it tells you how much the velocity changes every second. And we give the name acceleration to this quantity. So the definition of average acceleration is change in velocity over change in time. And it's seen by looking at the slope of an acceleration versus time graph. So what does it mean if this number is positive or negative? This number happens to be positive, meaning that the velocity is changing positively 0.1 meters per second every second. And the object happens to be getting faster. But the positive sign does not necessarily mean that the object's getting faster. The positive just means it's going up 0.1 meters per second every second. So if the acceleration is negative, it means the velocity is changing downward. But we'll see examples later on where that could actually mean an object's getting faster. So don't fall into the trap of thinking that positive acceleration means getting faster and that negative acceleration means getting slower. Now the area under a velocity versus time graph should still show us displacement, and I'll show that really quick. If I take a look at the area out to maybe 6 seconds here, on the velocity versus time graph, instead of the area being a rectangle, from 0 to 6 seconds, now it's a triangle. It's all of this stuff, which I'll try to shade in as quickly as possible here. But I think you'll see that the shaded in region here is a triangle. So the area being 1/2 base times height, that would work out to 1/2, the base being 6 seconds. The height from 0 meters per second to 0.6 meters per second is 0.6 meters per second. So look at the units. The units will still come out to meters because the seconds are going to cancel here and here. And if I do the math on this, 0.6 times 6 times a half, which is 0.5, that gives me 1.8 meters. So I'm getting 1.8 meters. That should be my displacement. Now let me go over to the position graph just to verify that. Here's 6 seconds over here. The object starts from a position of 0 at time 0. At 6 seconds on the graph, we're up here. And if I go over to the position, this says 1.8 meters. So the object travels from a position of 0 to a position of 1.8 meters. So we're verifying that the displacement is indeed 1.8 meters. And so we're getting that from the position versus time graph as well.